In today's video, I want to look at some more problems of limits. So we're going to look at one example where we're going to use the conjugate of an expression in order to help solve the limits. We've already looked at ones where we've had to factor, and we've looked at ones where we can just plug things in, which also happens in our factoring examples as well. We factor and then at the end we can just plug the point in. But I want to look at an example where we have to use the conjugate to solve the limit, and then I want to kind of guide us through an example that's going to lead you into Calculus 1 and the kind of things that you'll be looking at in Calculus 1 that will set you up for differentiation as you go through that at the start of Calc 1. So let's go ahead and do this example. I want to look at what's the limit as x approaches 4 of 2 minus the square root of x over 4 minus x. Now, like I said with our factoring ones, first thing you're going to do is just to plug the point in, just to see if there is continuity at that point. 9 times out of 10, whenever you get these limit problems, it's not going to work. So if we plug in x is equal to 4 into this, you can see we're going to get 0 over 0, which obviously doesn't work. So then our next inclination would be, okay, let's go ahead and try to factor. Well, we can't really factor an expression like this. We've got a square root of x in here. That makes it incredibly difficult to factor, so we can't use that. So what I'm going to do here is I'm actually going to multiply by the conjugate of the top. Okay, if I look at that numerator, I'm going to take the conjugate of that expression. That means that we change the sign of that second term, of that x term. So what I'm going to do to solve this is just to take my original expression and I'm going to multiply both numerator and denominator by the conjugate of this expression on top. The conjugate of this would be 2 plus the square root of x. So you're going to take that second term and you're going to change the sign of it. That is the conjugate. Okay, so when we do that and we multiply top and bottom by that term, that means that we are not changing our expression in any way. We're effectively multiplying by 1. So we're not changing it in any way, but it will help us to simplify it exactly like factoring helped us simplify our previous problems. So when I multiply two fractions, I just multiply straight across the top and straight across the bottom. So the top would give me 4. Then I would get 2 times the square root of x minus 2 times the square root of x, so those terms would cancel, and then I would get negative root x plus root x, which would give me minus x. Okay. Divided by, then I have 4 minus x, 2 plus the square root of x. Okay. I've got 2 4 minus x terms, they're going to cancel out, which just gives me 1 over 2 plus the square root of x. Now you may not find as much cancellation in some of these problems, but 9 times out of 10, if you've got a problem like this with a square root in it, I would highly recommend multiplying by the conjugate of whatever top or bottom has that square root in it, because normally it will help simplify something along the way to where we can now go ahead and just plug in. So whenever you get one of these examples where you've got a fraction that has a square root in it, multiply that term by the conjugate top and bottom. So whatever the conjugate of that term is, multiply top and bottom by that term, and then you can just go ahead and simplify like we have here. And now we can plug in x, okay? If we plug in x is equal to 4 into this, I get 1 over 2 plus the square root of 4, which is 2, which just gives me 1 over 4. Okay. So this is another type of problem where multiplying by the conjugate of one of the terms, top or bottom, can help. The other problem that I do want to go through before you go ahead and take a Calculus 1 course is an example that kind of brings a couple things together from this course. And that is bringing together these limits with a difference quotient. So if you remember, the difference quotient of a particular function f of x was this expression here. It was f of x plus h minus our f of x function divided by h. Okay. I'm going to do this for the particular function. F of x is equal to 3x squared plus 6x minus 4. Okay. I'll find the difference quotient for this function, and then we are going to look at the limit as h goes towards 0 of that difference quotient. Okay, so let's go ahead and figure out what f of x plus h is. So everywhere I see an x, I'm going to plug in x plus h. So that's 3 multiplied by x plus h squared plus 6 times x plus h minus 4. Multiply this out. And then if I do f of x plus h minus f of x all divided by h, I'm going to take what I have here for f of x plus h, I'm going to subtract f of x from it. So I'm going to take this term here and subtract this expression. Okay, so when I do that, the 3x squareds are going to cancel out, the 6x's are going to cancel out, and the negative 4's will cancel out. So on the numerator, I will end up with 6xh plus 3h squared plus 6h all divided by h. Okay. Now what I'm going to do is I'm going to take the limit as h goes towards 0 of this. Okay. Well, it turns out when we get to this point, you actually have a bunch of h's that cancel out. If I divide every single term here by h, it's going to cancel the h out there. It's going to cancel the squared out there because 3h squared divided by h just leaves me with 3h. And then 6h divided by h just leaves me with 6. So I'm looking at, once we've simplified that, I'm going to have 6x plus 3h plus 6. So at this point, looking at the limit as h goes towards 0, I can just plug in h is equal to 0, and I'm left with this expression here. Okay. So we started out with this function here. We found the difference quotient of that function, and then we took the limit as h goes towards 0 of that function. Okay, and then we ended up with 6x plus 6. What's the point in doing this? Well, as you will learn in Calculus 1, this expression here is actually going to be the slope at any particular x value of this function. So we've got this function, 3x squared plus 6x minus 4. Let's say that I am looking at the point x is equal to 1. Okay. At x is equal to 1, what's my function value? I would have 3 plus 6 minus 4, which would give me f at 1 equals 5. Okay, so I know that a coordinate on the graph of this function is going to be 1, 5. Okay. So let's go ahead and draw a quick sketch of this thing. This is just going to be a quick sketch. It's not going to have any of the correct x and y intercepts or anything like that. It's just a quick sketch just to show you what I mean when I talk about a slope here. So let's say that this is the point 1, 5 on my quadratic for the graph of this function. Okay, the point 1, 5 lies on the graph of 3x squared plus 6x minus 4. Okay, we just plugged in x is equal to 1, found what the f of x value was at that point. Okay. Well, when x is equal to 1, if I set x equal to 1 in here, I get 12. That tells me that the slope of this graph at that particular point, if I were to take a line, okay, the slope of that line that is tangent to that point, so just where it just touches that one point on that graph, the slope of that is going to be 12. That is the meaning of why we do all of this, why we use the limits with the difference quotient. And you will be doing all of this in Calculus 1. But that's what it looks at. It actually gives us the slope of the graph at any particular x value. So I can take any x value I want, let's say x is equal to 2, and then at x is equal to 2, I can find out what the slope of the graph is at that particular point. So I just take the straight line that just touches at that one point. What is the slope of that line? Well, we just plug in our x value for x is equal to 2 here. We would have a slope of 18. Okay, so each one of these x values will give me a different slope. All I have to do is just plug in each of the x values into this particular equation, and it will give me the slope at any particular x value for a graph.